Take a look at this lotus plant. It grows natively in slow-moving, heavily silted, and completely murky water. Yet, despite thriving in constant contact with mud and grime, the plant's broad green leaves remain immaculate. They never look dirty, and nothing seems to stick to them. For centuries, observers and botanists alike treated this as a random biological quirk, an oddity of the plant's natural habitat that required no further explanation. You can see in this close-up image how water behaves differently here. Instead of dampening the surface, rain pools into perfect spheres. Maintaining this level of absolute cleanliness in a filthy environment requires an active physical mechanism operating right in plain sight. In this photograph from the 1980s, we see German botanist Wilhelm Barthlott. He identified the lotus leaf's cleanliness as a specific engineering puzzle. Barthlott realized that our eyes were being deceived. Looking closely at the leaf, it appears perfectly smooth and flat, but that visible smoothness is a complete optical illusion. To understand how the lotus stayed clean, science had to strip away the macroscopic view and drop down into an invisible microscopic reality. When we descend past what the human eye can see, the familiar green surface disappears. It's replaced by a rugged, alien terrain. At this magnification, the architecture of the leaf becomes visible. The surface is entirely covered in tightly packed microscopic bumps called papillae, and looking closer at those ridges, each bump is coated in water-repellent wax crystals, measured in nanometers. It is this specific double-layered defense, the chaotic physical texture combined with the chemical wax, that creates a highly hostile landscape for any moisture trying to settle. Extreme repellence relies on exactly the opposite of smoothness. It requires severe microscopic roughness. To see how this architecture functions in practice, we have to look at the physics of a single raindrop landing on this jagged terrain. Because these tiny papillae bumps are clustered tightly together, the water droplet physically cannot penetrate the narrow gaps. It sits stranded on the peaks. By resting solely on the tips, the droplet seals off the valleys below, trapping a microscopic air layer underneath it. Now, instead of touching the leaf surface, the water is actually floating on a cushion of trapped air. With almost zero friction to hold it in place, it snaps into a perfect sliding sphere. As gravity pulls that frictionless sphere across the leaf, the water acts like sticky tape. It physically lifts and collects dirt, dust, and pathogens off the peaks and carries them away. This physical reaction is essential for the plant's survival. A leaf free of silt and mud absorbs maximum sunlight, ensuring uninterrupted photosynthesis even in heavily polluted waters. By engineering a highly specific surface texture, the lotus evolved a way to turn everyday rain into an automatic, zero-energy cleaning system. In 1997, Barthlott and his colleague Christoph Nienhaus formally published the mechanics of this microscopic architecture. They officially named it the Lotus effect. Their publication triggered a global race among material scientists. Laboratories worldwide started mathematically mapping the exact spacing, height, and width of the biological bump patterns. Soon, engineers managed to recreate the geometry in the lab. They manufactured synthetic surfaces that forced water and dirt to behave exactly as they did on the living plant. Humanity had successfully reverse-engineered a biological blueprint honed over millions of years, turning it into a mass-producible synthetic technology. The industrial applications arrived almost immediately. Manufacturers began mimicking the leaf's microarchitecture to develop exterior house paints that wash themselves and protective coatings that repel liquid metal during welding. This principle is applied in modern textiles. This image shows a synthetic fabric coated in microscopic roughness, forcing liquids to bead up and roll off so the material beneath stays completely dry. The principle is now utilized in massive solar fields. By applying lotus effect coatings to the glass panels, a light rain is all it takes to wash away the dust, ensuring the cells operate at maximum energy efficiency. A defense mechanism developed by a simple pondweed to survive muddy water is now quietly powering multi-billion-dollar global industries. Often, the most effective technological leaps do not require us to invent something entirely from scratch. We just have to look close enough at the invisible solutions nature has already perfected.